our distinguished guest, Filippo Camerota, who's the scientific director of the rather wonderful Museo Galileo of the river, and he's going to tell us all about how the Medici helped it to happen. Thank you very much.
Thank you. Thank you very much for the introduction, and thank you for the invitation in this conference. And thank you to Jonathan for sponsoring the lecture. He has been for many years a good friend of ours, of the Museo Galileo, and he translated a lot of our works, books, and exhibition catalogs. So we are very, very, very close. And we start with an image of the Museo Galileo. I don't know if you know the museum, I suppose yes. I hope yes. But it's an important museum, as you know, because it is a collection very well preserved, an historic collection. It's the collection of mathematical instruments put together by the Medici family in a period more or less 3 centuries. And it's very important because it tells the story of a special relationship between the arts and the science. The fact that these instruments were kept for around 2 centuries in the Uffizi Gallery, together with the masterpieces of ancient and modern art, also indicates precise desire to celebrate this distinctive sign of Medici patronage in the intellectual unity of the arts and the sciences. As we will see at the end of this lecture, the concept was definitely sanctioned immediately after Galileo's death by the desire expressed by the Grand Duke Ferdinand II to erect a monumental tomb for the scientist in the Basilica of Santa Croce, right in front of that of the great Michelangelo, the father of the arts. The brotherhood between art and science in Florence has ancient origins. One of the first examples can be found in the baptistry of San Giovanni, where an unknown 13th century astronomer collaborated with the artists who composed the splendid marble floor to transform the building into an astronomical instrument, precisely a solstitial sundial. As we read in the chronicles of Giovanni Villani, every year at midday on the summer solstice, a sunbeam penetrated from the opening at the top of the dome, then without a lantern, and illuminated exactly the figure of the sun carved in the center of the large wheel of the zodiac placed in front of the eastern door of the building. The astronomical event preceded by a few days the feast of St. John the Baptist, patron saint of Florence, but it is probable that the artifice did not only have a calendar function. The astronomer may also have used it to carry out precise astronomical measurements, as Paolo del Pozzo Toscanelli did in 1475 in Santa Maria del Fiore, using the lantern of Brunelleschi's dome as the gnomon of a gigantic solstitial sundial intended to measure the obliquity of the ecliptic. Toscanelli was in this image you see a couple of meridian line, actually. The first one, the one signed with 1475, of course, is the one made by Paolo del Pozzo Toscanelli. The other one was made 3 centuries later by Leonardo Ximenes, because in this time, probably there was a very small movement of the dome, the cupola, and the exact moment of this solstice, the summer solstice, was lost. So it was necessary to correct the meridian line. Toscanelli was the most famous astronomer in 15th century Florence. He was responsible for the first measured observations of comets, and it was he who drew up the drawing of the constellations that Giuliano del Rigo, known as Pesello, painted in fresco on the small dome above the altar of the old sacristy of San Lorenzo. a masterpiece of art, architecture, and science commissioned by Cosimo the Elder. The precise positioning of the planets and stars allows us to identify this representation as the exact configuration of the sky above Florence on 4th July of a year not yet identified with certainty. The most probable dates are 1439 or 1442. 1439, of course, is the most important year because it's the year of the Council of the Two Churches in Florence. So it has an historical importance. It explains eventually the reason why Cosimo the Elder wanted to fix this date on the cupola of the Sacrestia Vecchia. Toscanelli was also a close friend of Brunelleschi, whose engineering feat in building the dome of Santa Maria del Fiore made him the main reference point for his contemporary artists, architects, and engineers. Brunelleschi's effigy appears in a singular group portrait painted by Paolo Cello that seems to celebrate the partnership between art and science. In addition to Brunelleschi, we see in this painting Giotto, Paolo Cello himself, Donatello, and the mathematician Antonio Manetti. It is not so much the presence of the mathematician that indicates the link between arts and sciences, but rather the fact that all these characters were involved in the great artistic revolution of the 15th century brought about by the spread of linear perspective. Giotto was the first to experiment this new way to represent space, pictorial space. Although the geometric rules for perspective representation of space had not yet been developed, his paintings are strongly characterized by an innovative three-dimensionality based on the observation of nature. Paolo Cello was literally obsessed with perspective geometry, so much so that he committed himself to the design of very complex bodies, such as the so-called mazzocchio, a polygonal ring, usually with an octagonal section. Donatello was the inventor of perspective bas-relief, the so-called schiacciato, which means flattened, which allowed pictorial effects and profound spatiality to be obtained on a stone surface of very little relief. Antonio Manetti was a mathematician, commentator on Dante, a good friend of Paolo Cello, according to Vasari, but above all, the biographer of Brunelleschi, widely considered the father of perspective. It is thanks to Manetti's biographical information that we know in detail the characteristics of the two perspective panels that mark the birth of Renaissance pictorial perspective. These were two experiments or demonstrations that aimed to show the perfect correspondence between perspective representation and visual perception of reality. In the first painting, Brunelleschi had depicted the Florentine baptistry seen from the central door of the cathedral. The representation was very realistic, and to increase the resemblance of the real view, the sky was made with mirror-polished silver leaf, so as to perfectly reproduce the brightness, color, and any cloud formations. The observer did not have to look at the painting frontally, but standing behind the panel and looking through a hole, he would see it reflected in a mirror. The second painting depicted Palazzo Vecchio and the Loggia dei Lanzi seen from Via dei Calzaioli. In this case, there was no sky. The tablet was cut along the upper profile of the buildings so as to be able to optically superimpose it on the real buildings and verify the perfect correspondence of the real view with the painted one. From these demonstrations, the great season of Renaissance perspective painting began, in painting with the work of Masaccio, in sculpture with Donatello and Lorenzo Ghiberti, in literature with the fundamental treatise on painting by Leon Battista Alberti, which is not by chance dedicated to Brunelleschi. Alberti's merit is that of having established the conceptual principles of the new science of painting, simplifying the mathematical procedure to a simple expedient, the drawing of the floor as a modular grid from which to take measurements of the apparent reduction of objects in the depth of pictorial space. The floor was essentially a grid that provided latitude and longitude coordinates in the perspective space for each object. Piero della Francesca developed a more mathematical codification of the rules of perspective, illustrating operations that were not always necessary for pictorial practice, but were fundamental to understand how all forms, even natural ones, could be traced back to a geometric synthesis, such that they could be precisely measured and represented. The famous geometric construction of a human head is an exemplary case of this reasoning and shows how this, in this case too, it operates using latitude and longitude coordinates. Piero's head is not at all different, moreover, from the construction of a terrestrial and celestial globe, which allows one to measure distances and represent lengths and constellations through the same process of geometrization of the spherical body. You can imagine, you don't see the meridian and parallels in the Piero della Francesca's head, but you can trace them optically just following the numbers, for example. Painters were often also involved in drawing geographical maps, Francesco Rosselli, for example, and the rebirth of geographical studies seems to have produced a lively exchange of skills between artists and cosmographers. The German cosmographer Regiomontanus, for example, a friend of and correspondent of Paolo dal Pozzo Toscanelli, used Alberti's treatise on painting to explain the construction of Ptolemy's third cartographic method. Ptolemy's geography was rediscovered in Florence in 1397, when the Byzantine scholar Emanuele Chrysoloras, called to Florence to teach Greek, brought with him a Greek codex of the work that was thought to be lost. The Latin translation of the famous treatise gave rise to important geographical studies, which for the first time confronted the mathematical representation of the known world. In that work, Ptolemy thought how to draw the map of the inhabited world through three geometric methods that contemplate the flat peeling of the spherical surface, the first two methods, and a perspective representation of the Earth inside an armillary sphere. The updates to Ptolemy's geographical tables were favored not only by humanistic studies, but also by the commercial policies of the great powers, which shortly thereafter led to the discovery of the New World. Toscanelli was one of the protagonists of this story. He was responsible for the geographical studies that contributed to the success of Christopher Columbus' first voyage. It was the marine map, now lost, drawn by Toscanelli that indicated the route towards the west to reach the East Indies. Toscanelli also precisely indicated the distance to travel to reach the western coast of China, only to then discover that at that distance was not Marco Polo's China, but a new continent that had been totally unknown until then. Another Florentine protagonist was Amerigo Vespucci, navigator and cosmographer in the service of Pier Francesco de' Medici, and the first of the great admirals to recognize that the lands discovered by Columbus as parts of a new continent which then took its name from him. The cartographer Martin Waldseemüller portrayed him on the world map that gives its name to America in direct comparison with Claudius Ptolemy, a comparison not too different from the one mentioned above between Michelangelo and Galileo. Ptolemy's book also underwent a monumental elaboration in the Guardaroba Nuova of Palazzo Vecchio, where Cosimo I wanted to collect the most precious objects of his collection in cabinets decorated externally with the updated tables of Ptolemy's geography. The so-called maps room today shows only a part of what was the grandiose project conceived by Cosimo de' Medici, designed by Giorgio Vasari and developed on a cosmographic level by the cosmographers Miniato Pitti, Ignazio Danti, and Stefano Bonsignori. You can see the reconstruction, the virtual reconstruction of this room on our website. This is a new project we have just presented a few days ago in the occasion of the presentation of the restoration of the terrestrial globe. You see there the big terrestrial globe by Ignazio Danti. And in this virtual reconstruction, you can explore all the maps and you can read all the information written on that maps. I think it's a very beautiful way to know it, to study the old geography and old geographical knowledge. Above the wardrobes were busts and portraits of illustrious men, philosophers, men of letters, emperors, and ancient and modern princes. The constellations described by in Ptolemy's Almagest were to be painted on the ceiling, and thanks to a never-built scenic machine, two large globes, one celestial and one terrestrial, were to be lowered from the ceiling on command. Only the terrestrial globe was made by Ignazio Danti, but it was never placed in the room, whose work was interrupted following the death of Cosimo I in 1574. With the birth of the Grand Duke of Tuscany, under the leadership of Cosimo I, the experience of the Garden of St. Mark, promoted by Lorenzo the Magnificent to encourage the progress of the arts, was resumed and institutionalized. The foundation of the Accademia del Disegno in 63, protected under the aegis of the enlightened prince the realization of the artistic ideals of the Tuscan genius. With Cosimo as father of the men of drawing and Michelangelo as a spiritual guide, the Academy intended to affirm the primacy of Tuscany in the development of the three major arts. The excellence of painting, sculpture, and architecture, already celebrated in the historiographical work of Giorgio Vasari, was now entrusted to a complex educational program that was both practical and theoretical. The study of drawing, practiced in front of Michelangelo's famous sculptures in the new sacristy of San Lorenzo, was alternated with theoretical lessons on anatomy, perspective, geometry, and mathematics, which consolidated the traditional partnership between art and science implemented in Florence since the previous century. The statute of the Academy specified that the reader of mathematics is required to read Euclid's Elements and give lessons on perspective or mechanics or other practical geometry. Mathematics teaching at the Accademia del Disegno was inaugurated in 1569 and was held every Sunday. The lectures were held by some of the most eminent mathematicians of the Medici court, including Ignazio Danti, the first Medici cosmographer, and Ostilio Ricci, Galileo's teacher. Ignazio Danti was one of the protagonists of the calendar reform promulgated by Pope Gregory XIII in 1581. His astronomical studies to correct the ancient Julian calendar began in Florence on behalf of Cosimo I. The astronomical instruments installed on the facade of Santa Maria Novella served this purpose, a quadrant and an equinoctial armillary that were used to observe the exact moment of the equinoxes. He also designed a camera obscura sundial to measure the exact moment of the solstices inside the church. This last instrument was never built, but he did it in the Basilica of San Petronio in Bologna, where he moved before going to Rome in the service of Pope Gregory XIII. The attention paid by Danti to the mathematical training of artists is demonstrated by his important works in disseminating mathematical sciences. In 1573, he published the first Italian translation of Euclid's Optics, the fundamental text that had guided the progress of the science of vision since the Middle Ages. In the dedication, Danti lamented the sharp decline in interest in this discipline among the scientists, maintaining that to learn the principles of perspective, that is, optics, previously a subject of study for philosophers, it was necessary now to study them among mechanical craftsmen, namely the painters. Painting, sculpture, and architecture were included by Danti among the mathematical sciences dependent on geometry. And this explains the reason for his commitment to editing and commenting on one of the most famous treatises on perspective for painters, The Two Rules of Practical Perspective by Giacomo Barozzi da Vignola, a book on which he made extensive use for his perspective lessons at the Accademia di Disegno. Vignola's treatise with Dante's commentaries represented an almost definitive text on the science of painters. To the practical rules of drawing codified by Vignola, Dante had in fact added long mathematical comments that consolidated scientific foundations of drawing. But he also collected various tools for drawing from life, inventions of artists, mathematicians, and military technicians. In fact, among the painter's tools, it also includes a singular surveying instrument invented for Cosimo I by the Medici engineer Baldassare Langi. The instrument, now in the Galileo Museum, allowed topographical maps to be drawn up also through the drawing of perspective views, and represented a real innovation in the instrumental technical field. I think this is one of the most beautiful instruments we have in the museum. It's very refined in construction, but it's also refined in its operation, actually. It's a surveying instrument, but it allows to draw perspective views, not just for pictorial purposes, but in order to use the perspective representation for later obtaining the plan of the fortress. In this case, it was a military instrument, of course. It was used during the sieges for taking a shot, a picture, a photograph, if you want, of the fortress, and then from that image the plan of the fortress. And the plan was a fundamental drawing to organize better, the best, a siege of a castle or a fortress. The strong curricular imprint given to the Accademia del Disegno was further strengthened by the 1578 proposal for the teaching reform made by Federico Zuccari, who insisted on the importance of teaching perspective and mathematics to the young artists. His portrait with a table of geometric figures and proportions of the human figure is quite eloquent about the scientific culture of the artists, as it is the allegorical apparatus sculpted on the facade of his home studio, showing the attributes of the arts of drawing, where compasses and surveying instruments are depicted among the tools, or better, sculpted among the tools of the three major arts. The practical teaching of Euclidean geometry dominated the mathematical culture of the 16th century, giving rise to the training of professional figures who easily carried out both artistic and technical work. Painting, cartography, architecture, fortifications, and machine building were often skills identifiable in the same person, whose mathematical training was increasingly assisted by schools closely linked to the artist workshops, such as the private ones held by Ostilio Ricci and Giulio Parigi. Ostilio Ricci arrived from Fermo to Florence around 1580, perhaps immediately entering the Florentine artistic circles thanks to the friendship of Bernardo Buontalenti. In Buontalenti's house workshop, Ricci held geometry and perspective lessons to the young artists who frequented it. Among these were Ludovico Cigoli, Giulio Parigi, and Giovanni de' Medici, who perhaps was the intermediary for the official position given to Ricci as mathematician at the Medici court. This role would then also be covered by Galileo, who, as a student, was introduced to the study of Euclidean geometry by Ricci himself. During the period in which Ricci was reading Euclid at the Accademia del Disegno, the Grand Ducal cosmographer Antonio Santucci delle Pomarance gave cosmography lessons to the artist. The great Ptolemaic armillary sphere built for Ferdinand I in 1593 was a cosmographic monument that dominated a room in the Uffizi Gallery, a room specifically dedicated to cosmography. In the room, there was also the large terrestrial globe that Ignazio Danti had made for the maps room of Palazzo Vecchio, the place where Cosimo I intended to glorify the science of cosmography, and with it, his own name, Cosimo, whose Greek root is precisely cosmos. This beautiful armillary sphere is now visible at the Museo Galileo. I think it's a unique object. Not really unique. There is another one very similar, a little bit smaller, but older, because it's the older sister of this armillary sphere. Was made few years before that, this one, by the same cosmographer in Rome for the Ferdinando de' Medici when he was a cardinal. And it was given as a present to Philip II in Spain by Ferdinando de' Medici. And now it is in the library of the Escorial in Spain. And I would like to have the occasion one day to organize an exhibition with the two sisters put together in the same place. I think it's difficult, but we can do eventually that virtually. During the period in which, can you hear me? Yeah. Excuse me. In the Uffizi Gallery, founded by Francesco I in 1581 as a temple of ancient and modern art, Ferdinand I had another room dedicated to mathematical sciences, which was called Mathematics Room, or better at that time, Military Architecture Room. Military architecture was, in fact, the discipline toward which the various mathematical sciences converged, of which the instruments kept in the room were representative: arithmetic, geometry, topography, mechanics, astronomy. They were the instruments of the collection started by Cosimo I, expanded by Ferdinand I and subsequent Grand Dukes, and today kept in the Galileo Museum. The first custodian of the mathematical collection was a painter-mathematician, Giulio Parigi, a pupil of Buontalenti, and author of the decoration of the ceiling, in which many of the most significant instruments in the collection are depicted. He was also entrusted with the position of mathematician of the pages, Giulio Parigi, after the death of Ostilio Ricci. It was the first time that that position had been entrusted to an artist. Following the example of Ostilio Ricci, Parigi opened a school in Via Maggio near Buontalenti's house, where the young people of the Medici family and the Florentine nobility also studied. According to Filippo Baldinucci, who defined this school as an academy, Parigi, I quote, read Euclid, taught mechanics, perspective, civil and military architecture, and a beautiful and new way of drawing very nice landscapes. This academy was not only attended by 7 of his children and by all the Florentine nobility, but it had already become so famous throughout Europe that Italian and ultramontane princes and great knights came on purpose and settled in our city to learn those noble sciences and disciplines." End quote. The teaching of measuring methods certainly included a series of practical exercises, of which Parigi himself offers us an example in a lively cartoon where the place of the exercises is the courtier's place in Piazza della Signoria, formerly the theater more than a century earlier of the mathematical demonstrations of the abacist Pier Maria Calandri, and even more distant times on the famous perspective demonstrations of Filippo Brunelleschi. The teaching of perspective, in particular, also involved the use of tools that Giulio Parigi depicted in one of his manuscripts, now preserved at the Library of Congress in Washington. This manuscript is particularly important because it collects exercises and problems relating to all the subjects taught in the Parigi school: plain and solid geometry, topography and cartography, artillery, mechanics, stage set design, military architecture, measuring techniques, and drawing techniques. In the latter case, different tools for perspective drawing are depicted. We found here one of the most singular instruments of the Medici collection, still visible at the Museo Galileo, the already mentioned surveying and perspective instrument by Baldassare Lanci. Another instrument depicted is an invention of Bernardo Bontalenti, which we also find depicted in another manuscript of Giulio Parigi, and also depicted in fresco on the ceiling of the on the ceiling of the mathematics room. The third tool in this manuscript is an invention of the German goldsmith Wenzel Jamnitzer, invented to draw geometric bodies in perspective not from life, but from a plan and elevation drawing. This special drawing was known through this beautiful engraving, but apparently this engraving was not so common. It was quite rare in that period. And in fact, we find, sorry, something is happening here. We find the instrument drawn by Ludovico Cigoli, this sketch here, just to memorize the characteristic of this instrument. Okay. Another instrument is an adaptation to the perspective drawing of a bomber targeting instrument. Usually much smaller, this artillery tool was used to establish the elevation of the cannon. Another instrument is an invention by Ludovico Cigoli, which the Florentine painter illustrated fully in his treatise on particle perspective a few years later. Then we find, this is Ludovico Cigoli with this special instrument. Then we find the glass, so-called glass, that was illustrated in print for the first time by Albert Dürer. But we know that it was already previously used in painters' workshops. Leonardo illustrated it, and it was the tool that best expressed the concept of painting as a window, according to Alberti's well-known definition. The most famous perspective drawing in the Renaissance was certainly the so-called door, sportello, invented by Albert Dürer and described by Ignazio Danti. And this instrument was quite widespread in artists' workshops. And an example, well, this is the engraving by Dürer, and we find also an example of this instrument in the mathematics room, showing the use of the instrument for drawing a fortress. This was clearly one of the most important applications used of these instruments, because it was linked with the military science. Here we have a demonstration in one of the perspective treatises of that age of the way to obtain the plan of the fortress from a perspective drawing. This is not a tool, but a technique of perspective deformation of images, now called anamorphosis, which is starting to be quite widespread in this period. Daniele Barbaro, one of the most important writers on perspective in the 16th century, had called it secret perspective. In the 17th century, it became the subject of study of the French mathematicians, especially Jean-François Miseron, who was the theoretician who dedicated a couple of treatises very important to this perspective technique. We then find a singular invention of for enlarging drawings developed by the mathematician Giovanni Battista Vimercato and described by Daniele Barbaro again in his treatise on perspective. And then the experience of the camera oscura that began to be widespread in the beginning of the 16th century. It is mentioned by Leonardo and described by Cesare Cesariano in his commentary on Vitruvius De Architettura. Barbaro again called it a natural perspective because it was a painting made by nature, light of the sun, of course. Giovanni Battista della Porta includes this instrument among the phenomena of natural magic. Ignazio Danti talks about it in relation to the gnomon of Santa Maria del Fiore and indicates the way to straighten the image with a flat mirror inclined at 45 degrees. Ludovico Cigoli speaks of it as the instrument that allowed the first man to learn the art of painting and compares its functioning to that of the eye. The spherical mirror is mentioned as a tool for straightening images in the dark room. The effect is shown here. If the object is closer than the focal point, the image is straight. If it is farther away, the image is enlarged and reversed. The camera oscura was not a practical tool for the representation of close objects, since focusing problems generated a whole series of distortions that excessively prolonged the time required to create drawing. Instead, it was unparalleled for the representation of distant things, so much so that its success was recorded above all in the field of pictorial and cartographic landscape painting. Think about Canaletto, for example. With the improvement of the telescope, however, the camera obscura favored a very particular use as an instrument for the scientific representation of astronomical observations. The first to use it methodically were Galileo and his painter friend Ludovico Cigoli. Galileo considered Cigoli as one of the greatest authorities of his time on pictorial matters and was able to make use of his precious collaboration in the representation of the moon and sunspots. Some of Galileo's most inspired reflections on the figurative arts are contained in the exchange of letters with Cigoli, who in turn considered Galileo as his own master of perspective, perhaps referring to the subtle optical considerations traceable in the pages of Desiderius Nuncius. The last years of Cigoli's life, when the artist worked more assiduously on the drafting of his treatise on practical perspective, are marked by an intense correspondence with Galileo. The letters are largely dedicated to the observations of sunspots. You can see some examples here that the painter methodically carried out in support of the contemporary investigations of Galileo. The drawings attached to the letters illustrate the position of the sunspots that Cigoli transcribed day after day inside a circle traced on the drawing paper, tracing the image of the sun projected by the telescope in a dark room, according to a method devised by a disciple of Galileo, Benedetto Castelli. For this purpose, Cigoli also meditated on an improvement of the telescope, imagining a ruler combined with the instrument, which would guarantee the accuracy of the graphical transcription, allowing the light beam to be projected onto a plane constantly in axis with the telescope while it rotated to follow the course of the sun. The attention paid to perfecting the telescope is equal to that dedicated to the development of the perspective instrument that Cigoli illustrates in his treatise on perspective. The purpose of the invention was to facilitate the representation of distant things, an operation in which the insufficiency of geometrical rules and the arbitrariness of the artistic execution were promptly noted. The sun and the moon were certainly the most distant objects one could imagine, and the telescope was the most suitable instrument for observing and representing them. The drawing of the phases of the moon, usually attributed to the hand of Galileo, are the most exciting testimonies of this particular partnership between the astronomer and the painter. Similar drawings, if not exactly these, as some scholars suspect, were certainly made by Cigoli in preparation for the great fresco of the Immaculate Conception, which he was painting in those years on the dome of the Pauline Chapel in Santa Maria Maggiore in Rome. Under the feet of the Virgin appears a moon, different from the one handed down by Marian iconography. No longer a white and immaculate moon, but a celestial body tormented by numerous craters, the very ones that Galileo saw for the first time and punctually described in the Sidereus Nuncius. The moon is no longer a symbolic image, but a portrait from life, painted by a painter at the height of his artistic maturity with the aid of the optical instrument that would revolutionize the conception of the world. The letter in which Cigoli announces that he wants to build a ruler to better use the telescope in representing sunspots also contains a preview of the parallel between Galileo and Michelangelo, with which we open this lecture. And I would like to close with the reading of this passage. Referring to the criticism directed by Galileo by his detractors, Cigoli expresses himself in these terms, quote, "I believe that the same thing is happening as when Michelangelo began to conceive architecture outside the order of others up until his time, where everyone unitedly said that Michelangelo had ruined architecture with many of his licenses from Vitruvius' rules. Therefore, hearing some of them, I replied that they were wrong, because Michelangelo had not ruined architecture, but the architects, because if they did not have the same inventive capacity as him, they would fall into the precipice. And if they made their buildings as before, so simple, they appeared trivial things." End of quote. The comparison between Galileo and Michelangelo had an interesting sequel after the scientist's death, when Grand Duke Ferdinand II expressed the desire that a monumental tomb be erected for Galileo in Santa Croce, right in front of Michelangelo's tomb. Due to the restrictions imposed by the church after Galileo's trial, the tomb was erected only in 1737, thanks to the commitment of the scientist's last disciple, Vincenzo Viviani, who in his biography of Galileo makes explicit the message contained in that monument. As anyone could read, on the facade of Palazzo Viviani in Via Sant'Antonino, where Galileo's life and work is exposed to the public domain through a large marble cartouches, Galileo was born in Pisa on 18 February 1564, just as in Rome, that same year and that same day, writes Viviani, Michelangelo died. Galileo was actually born on 15 February, but the desire to underline the mirror image between the two great men, the passing of the baton, or the reincarnation of the genius of the arts into the genius of the sciences, led Viviani to falsify the date of birth to better express the concept. In the initial project, Galileo's tomb was to have even the features of that of the great Buonarroti. And a further parallel was to be seen in the allegorical statues that accompanied the busts of the two great geniuses, architecture, painting, and sculpture for Michelangelo, astronomy, geometry, and philosophy for Galileo. Art and science, which had been sisters in Florence for 3 centuries, were now represented in monumental form in one of the most important churches in the city. Thank you.
And as always, we now open up for questions and comments, and same rules. If you're in the room and want to speak, put your hand up. I'll bring you a microphone and everybody can hear you. If you're on the Zoom, you can put your thoughts in the comments and I'll read them out on your behalf. Or if you're feeling brave and want to talk to us, just unmute and talk to us and we'll hear you. So that's how it works. So, anyone want to go first? Any thoughts in the room? Yes, we have one here.
Filippo was perhaps over modest about the treasures that can be viewed at the Museo Galileo. He showed us a few, but I would make 2 comments on that. First, for the objects themselves, one of the most extraordinary, I would say, meeting grounds between art and science is the collection of blown glass scientific instruments, thermometers, barometers, and all sorts of vessels, which when the museum was renovated in 2012, were installed, 2010, sorry, were installed with an incredible, I don't know how many meters long,
5
glass, 5
5
meters
meters
long glass case, where they're really, I mean, it's glass meeting glass, and it's also art meeting science, because as I understand it, most of the objects were made in the Botany Gardens by glass blowers who were brought in from Venice by the Medici. So that's really a must see.
That's interesting. This is one example where science was used, or for to create an object of art, an artisanal object, very refined, because because
for the Valsimula world map and everything that you can read online, if you can't visit the museum, or when you do, but after your visit, do visit the website, where there's an extraordinary array of specific sites where you can find out about many of the objects.
We use very much the multimedia techniques for language, for explaining, for the valorization, or to explain at the best the scientific concepts. And Valsemüller map was one of that approach. Valsemüller map is not our object. It's an object, a unique object, preserved at the Library of Congress in Washington. But the link is Amerigo Vespucci, who is our man, of course. It's the link between Florence and America was very strong in that age, because of the discovering of the New World, where Amerigo Vespucci and Giovanni da Verrazzano, the Florentine navigators, were absolutely protagonists of that story.
It does remain an extraordinary thing that for the 200 years from 1400 to 1600, there was just this extraordinary proliferation of very brilliant Florentines who achieved all kinds of things. But I think interesting, and it's very strong in your lecture, that these brilliant men and women who were less celebrated but were also there doing their thing, there was not the modern distinction between the different disciplines wasn't there. They had these curious, intellectual, open minds, looking back to rediscovering the lost ancient learning, and then saying, okay, well, how do you fly how can you fly, or let's learn to really paint a portrait well. And it's all the same process. It's a very modern concept. We start specializing and separating out. So my question on the right observation is, do you know when this sort of the specialization started to happen and get more rigid as we now have it? But I'm an artist, I don't understand anything about maths, or I'm a scientist, I don't know how to put it. Do you know what
it happens with the Illuminismo, you know, the Enlightenment culture in the late 17th, 18th century. But above all, I think it was the beginning of the 20th century that started to separate cultures in this strong way. Even in schools, in the universities, you know, the necessity to have, you know, architecture, engineering, and geology, and all these disciplines separated was very strong, and was dictated probably by the specialization on many professions. And we see the same thing with our museums, because we preserve the mathematical instruments of the Medici, but La Specola preserves the natural collection, natural history collection. Those two collections were together at that time, the same places. So there is a necessity now probably to separate cultures for practical reasons, I don't know. But our challenge now is to put them together again in order to better understand what happened in the Renaissance and the other centuries, because otherwise you don't have a very clear idea of the culture of the time if you don't put together the disciplines and you can see the work.
In my generation in England, elsewhere in the West, was required to choose at the age of about 15 or 16 whether you were going to do arts or sciences. And if you chose arts, then it was almost an obligation to retain a pristine ignorance of anything. So that's a very weird place to have arrived. But
no, you're right. But you know, in the Renaissance, the good way to put together mathematics and painting, for example, was that of the developing the rules of perspective representation. Because in that case, you, as a painter, you had the possibility to represent reality as it appears. So you can give a wonderful representation of what you see. But in order to do that, you have to use geometrical rules and to learn how to represent things using mathematics or better geometry. And so this was the way in which many painters started to love mathematics. Before they didn't need that because the representation, the painting representation, followed other way to communicate with people, was much more abstract. So the Byzantine art was made of concept, no, very flat forms, shapes. Renaissance was looking at something else, and this was the way to to learn. There were of course people very skilled and very prepared in mathematics. Piero della Francesca was an extraordinary example, but because he was a mathematician in his mind, and the wonderful painter. And in fact, what he did as a painter, it can be understood only if you look at Piero also as a mathematician. You can appreciate the geometrical structure of his figures, no? Yeah, in fact. So.
What else want to join in this conversation?
Yes, separation between art and science, of course. In later centuries, you have the problem of the scientific disciplines themselves splitting up, and that leads to situations like the two museums in Florence. But I suppose an idea that had a powerful hold on the imagination in Galileo's time was the notion that the universe was mathematical. In other words, saying that you could only understand the universe through mathematics meant that I suppose if you wanted to depict it in any credible way, you had to be knowledgeable about the rules, the form, the rules of mathematics.
And now we have a whole virtual world which is entirely constructed by mathematics.
Thank you so much for your talk. Did any of these concepts of mathematics place pressure on a theological world? Or was it just
you know, the story of Galileo is representative of this. Of course, he had the the idea to explain the real world through mathematics, and he used the telescope as the instrument that showed exactly that mathematical calculation what you see through the telescope was a demonstration of the mathematical calculation made by another astronomer who was Copernicus, for example. Copernicus made a mathematical hypothesis explaining that the Earth is not in the center of the universe, but is the sun, which stay in the center. But he, used that argument only on a mathematical level, just to explain that calculation could be made better if you imagine the sun in the center. And he had he never pretended to say that that was the reality of the world. And this was why Copernicus didn't have any problem with the church. But Galileo went a little bit ahead. After the improvement of the telescope, he could demonstrate that the sun was in the center because what appeared in the sky was saying exactly this. For example, the phases of Venus. We don't see Venus as the moon. For example, we see Venus as a luminous point in the sky. But if you look with a telescope at this planet, you see that there are phases like the moon, and this explains that the Venus is rotating around the sun, and we're looking at it from outside this center. And this is one of the demonstrations that were saying that the world is exactly as Copernicus hypothesized in his time. In that case, but in that case, the troubles began for Galileo because, of course, he was pretending that the world was exactly that, and is not this world that was told by the sacred texts. So in this way, there was a big contrast between mathematics and theology. So the church had to defend the theological view of the world, and scientists had to defend the mathematical view of the world. But there were men of, some of the Jesuits, for example, who were wonderful, incredible astronomers, very clever, very well prepared, and they were in contrast with Galileo in part for the theological reasoning, in part because the instruments they used were not the same of Galileo. If you try to look through the Galileo telescope in our museum, we look with this. We use the telescope to look through and to watch something very far, especially the moon. But what you see is very frustrating because it's a small object at the end of a tube. It's not exactly as you can see with a simple binocular today. And if you don't have a very polished and perfect lens, you don't see what Galileo So, and what you can read in Desiderius Nuncius. And the Jesuits had imperfect lens at their disposal, so they couldn't see the same thing that Galileo saw. So there were practical problems. Then, of course, the theological problems were very strong, and the trial of Galileo, of course, was on that side, not on the mathematical side. But so there are different level of knowledge and a different way to look at the world that have to be eventually put together and related in order to understand the reality where we live. So this is one example of how mathematics and theology were in contrast or not, just they meet in some point.
And so Galileo was in a lot of trouble.
Yes.
Curious what the attitude of the Medici sponsors of Galileo was when Galileo was in trouble with the Church of the Medici. Abandonment? Or
No, not at all. But they had to be very careful because, of course, of you know, a relationship between the church, two states, two powers, and but they didn't abandon him. In fact, Galileo was not burned. He was put in a prison, in a wonderful prison, which is the Villa Il Gioiello here on Cetri. But of course he was he had to yes, exactly. And so it was forced to do that because otherwise it was a real trouble, that one. No.
Humans are very quiet. They're listening. I was messaged. Time to make their weekly contributions. All righty. So I think we seem to be coming towards the time to adjourn next door for a glass of delicious wine from us. Seasoned partner, Poggio Torselli. Strongly recommend visit there. The wine's good, but the place is beautiful. Yes, thank you, and thank Jonathan Mann again for all your sponsorship. And thanks again.
Of course, you are all invited to Galileo.